Okay, this is the second video on section 2.3. We're going to be looking at the definition of projection and vector components. Note, vector components is not the same thing as the component form of a vector. So these are different. So vector components, we're talking about an orthogonal component and then a component along another vector separate from the vector that we're talking about. So let's go ahead and look at this, and of course we're talking about non-zero vectors. So let u and v be non-zero vectors, and suppose that vector u can be written as w1 plus w2. Those are two vectors where w1 is parallel to vector v, and w2 is orthogonal to vector v. So w1 is called the projection of u onto v, or the vector component of u along v. The notation w1 is equal to proj, or projection of u onto v, and then we'll see how we come up with the formula. The projection of u onto v is equal to u dot v over the magnitude of v squared, and that's in parentheses, so that whole thing is a scalar, and then you have v there, so that gives you the direction of v. To find w2, the orthogonal component, w2 is going to be equal to u minus w1, and it's called the vector component of u orthogonal to v. So let's see what we got going on here. So we'll draw two vectors, vector u and vector v, and so we're going to look at the vector component along vector u, or parallel to vector the vector component parallel to vector v. So there's our w1, and then our orthogonal component would be w2. Okay, and notice if you add those, so w1 plus w2 gets you to vector the terminal point of the vector, so this looks good. Okay, so let's see what we got going on here. So w1 is equal to the projection of u onto v. Let's go ahead and look at theta. Theta is going to be the angle between u and v, or the angle between u and w1. So we're going to look at the cosine of theta is equal to the magnitude of w1 over the magnitude of u. So we're just looking at it as adjacent over the hypotenuse, so we're looking at a right triangle here. Okay. So then the magnitude of w1 is going to be equal to, because we're defining w1 as the projection of u onto v, and that is going to be equal to magnitude of u times the cosine of the angle in between them. Okay. Alright, well, the cosine of theta is equal to also u dot v over the magnitude of u, magnitude of v. So we're going to make that replacement. So the magnitude of w1, which is equal to the magnitude of the projection of u onto v, is equal to the magnitude of u, and then we're going to replace the cosine of u dot v. I'm sorry, we're going to replace the cosine with u dot v over the magnitude of u, magnitude of v. Okay, so that's going to give us u dot v over the magnitude of v. So w1 is equal to u dot v over the magnitude of v, and then we want to, w1's in the direction of v, so it's going to be parallel. So the u dot v over the magnitude of v, that is the c when we have parallel vectors. So we would have get a right color here. We'd have w1 is equal to cv, and we already know what the magnitude is. It's u dot v over the magnitude of v. So we want it to be in the direction of the v, so that's why we have the v here. But I don't want to mess up the magnitude here, so if I do multiply by or yeah, sort of multiply, yeah, it would be multiply v over the magnitude of v. That's a unit vector, so that's not going to affect anything. So this is a scalar, and this is a scalar, and so, yeah, I suppose it's a multiplication. And it's a scalar multiplied by a vector. And so that gives us u dot v over the magnitude of v squared in the direction of v. So let's go ahead and apply this. So example number 5, find the projection of u onto v and find the vector component of u orthogonal to v. And that vector component of u orthogonal to v is going to be w2. So vector u is 9, 7, and vector v is 1, 3. The projection of u onto v is going to be u dot v over the magnitude of v squared in the direction of v. So we need to find u dot v, so 9 times 1 plus 7 times 3 is going to be 30. And the magnitude of v squared is going to be 1 squared plus 3 squared. Okay, common error I see, and sometimes I do it too, is don't forget the square. Okay, so when things aren't working out, when you're finding the projections, sometimes you just forgot the square. Okay, so that's going to be 10. So we have 30 over 10 in the direction of v, which is 1, 3. And so this is going to be 3, 9. So that is the projection of u onto v. And that's your w1. To find w2, you simply take u minus w1, and that's going to give you your orthogonal component, orthogonal to vector v. So we have 9, 7 minus 3, 9, so that's going to give us 6 and negative 2. Okay. All right, and for part B, we're going to be looking at the same thing, but we got vectors in 3 space. I plus 4k is u, v is 3i plus 2k. Both of those do not have a j component. The projection of u onto v is going to be u dot v over the magnitude of v squared in the direction of v. So u is 1, 0, 4, v is 3, 0, 2. So when we do the dot product, that's going to be 1 times 3 plus 0 times 0 plus 4 times 2. And that's going to be 11. The magnitude of v squared is going to be 3 squared plus 2 squared under the square root, or 13. Okay, so that is going to give us 11 over 13 times the vector 3, 0, 2. So that's going to give us 33 over 13, 0, and 22 over 13. Define the orthogonal component. W2 is going to be u minus W1. So 1, 0, 4 minus 33 over 13, 0, and 22 over 13. So that's going to give us negative 20 over 13, 0, and 30 over 13. Okay. All right, let's look at the projection again. Okay. So projection using the dot product. If u and v are non-zero vectors, then the projection of u onto v is projection of u onto v is u dot v over the magnitude of v squared in the direction of v. And so we're going to look at coming up with this formula a little bit differently. Okay, so here's vector u and vector v. There is the projection of u onto v, w1, and then our orthogonal component, w2. Okay. So vector u is equal to w1 plus w2. Now w1 and v are parallel, so there exists real number c such that w1 is equal to cv. So we'll make that replacement. So u is equal to cv plus w2. And then what we're going to do is we're going to do the dot product with V on the right-hand side with everybody. Okay. So we got U dot V is equal to C, and then V dot V is magnitude of V squared. Okay. And then we'll make a mention that W2 and V are orthogonal. And when you dot product two orthogonal vectors, the result is 0. Their dot product is 0. So C is equal to U dot V over the magnitude of V squared. And so we knew that W1 was equal to CV. Well, we figured out what C is. It's U dot V over the magnitude of V squared in the direction of V. Alrighty, we're going to do an application or two, and that'll be it. So maybe this video will be a little bit shorter than the last one. Okay, so example number 6. I imagine that quite a few of you have been taking university physics, so probably you've seen stuff like this before in university physics. So our approach may be a little bit different, but it's going to be very similar. Example number 6 says, suppose a 5,400-pound truck is parked on an 18-degree slope. Assume the only force to overcome is gravity. Find the force required to keep the vehicle from rolling down the hill and the force perpendicular to the hill. Okay, so here's our hill with 18 degrees. And then I'm just going to draw a dot for the truck. And then there's its force going down. And that force would be 0, negative 5,400. And the magnitude there would be 5,400 for the pounds of the truck. Okay. We're going to go ahead and we're going to project this force onto the slope. So how much of that goes to the slope, or how much goes onto the slope there, and that would tell us how much we would force we would need to keep the truck from rolling. Okay, so vector U is going to represent the slope. So U is just going to simply be cosine of 18 degrees and sine of 18 degrees. And that's going to be very nice because when we find the magnitude of EU, that's going to be cosine squared of 18 degrees plus the sine squared of 18 degrees under the square root. And if you recall that cosine squared plus sine squared, that's Pythagorean identity, so it's going to be just 1. So square root of 1 is 1. So that'll be nice. And again, that is why we like the unit vectors. Okay. All right. And so there is our W1 on our picture, and it is parallel to U. They're pointing in opposite directions, but they're still parallel. They're just off by a constant. And then we'll highlight the W2. Okay. And so that's going to be the part orthogonal to the slope. So I didn't need all my extra slope there, so I couldn't raise it. Okay, so W1 is equal to the projection of the force onto the slope U, which is going to be U dot F over the magnitude of U squared in the direction of U. So U dot force is going to be negative 5,400 sine of 18 degrees. The magnitude of U is going to be 1. So W1 is equal to 5,400 sine of 18 degrees in the direction of U, which would be cosine 18 degrees, comma, sine of 18 degrees. Alright, so that's equal to negative 5,400 sine of 18 degrees, cosine of 18 degrees, and that's the first coordinate of our vector. And then our second coordinate of our vector is going to be negative 5,400 sine squared of 18 degrees. So we got our vector. And find the force required to keep the vehicle from rolling down. So that would be finding the magnitude of W1. So let's go ahead and find that. So the magnitude of W1 is going to be the negative 5400 sine of 18 degrees, cosine of 18 degrees, and then that's squared, plus negative 5400 sine squared, 18 degrees squared, and then the square of that whole thing. Make sure your calculator's in degrees here, and that's going to be about 1,668.7 or 8. I think it's 0.89 pounds. Okay. And what else they want us to find? They want us to find the perpendicular force to the hill or the slope there. So let's go ahead and find that. So that's going to be looking at W2. So W sub 2 is going to be the force minus W1. That's going to be 5400 sine of 18 degrees, cosine of 18 degrees, comma, negative 5400, plus 5400 sine squared of 18 degrees. And we'll go ahead and we'll find the magnitude of that. Okay, and calculating that again, and that's going to be 5,135.7 pounds. Okay, and so we found the force on the slope and the force perpendicular to the slope. It will satisfy the Pythagorean identity. 5,400 squared. That's the force. So we got a right triangle here. Would be approximately. We have rounding, so 1668.89 squared plus 5135.71 squared. So it would satisfy the Pythagorean theorem with the forces there. It's not going to be exact because we did some rounding there. Okay. And so we got one more thing to look at here. We're going to look at work, and then we'll do an application. So work is equal to force times distance, and we looked at that in Calculus 2. Work W done by a constant force F acting along the line of motion of an object is given by W is equal to the magnitude of the force times the distance, or the magnitude of F times the magnitude of PQ, and that would be the distance. We'd find the distance vector there. So we'll just take a box here. There's P and Q, and our force we're applying there, and then that's the situation we have there. Now, something a little bit more interesting is what we got in the second picture here. And it says when a constant force F is not directed along the line of motion. So the first one was work done by a constant force F acting along the line of motion of an object. So we're pulling the box forward, and the box is going forward. But maybe we have a string attached to it, and so we're not pulling it exactly in the same direction. Maybe we're pulling it up. We have a little bit of a different situation. So when the constant force F is not directed along the line of motion, then your work is going to be equal to the magnitude of the projection of F onto the vector PQ times the magnitude of PQ, which is also equal to the cosine of theta, which would be the angle between the line of motion and the force applied, times the magnitude of F times the magnitude of the vector PQ. Or simply vector F dot vector PQ, and that's the form we're going to use. It's going to be the easiest of them. So let's go ahead and draw our boxes again. So there's our P and our Q, and the line of motion is here, and then our force is not quite applied in that direction. Some of it will be applied in that direction. We'll look at the projection W1. Okay, And so let's go ahead and look at that. So there's theta and right angle, and we got the magnitude of the force here and the magnitude of W1 there. So the cosine of theta is going to be equal to the magnitude of W1, that's the projection of F onto PQ, divided by the magnitude of the force. So the magnitude of the force, cosine of theta, is equal to the magnitude of W1. The magnitude of W1 is simply the projection of F onto the vector PQ, so there'd be the projection of F onto the vector PQ. So work is, if you recall, force times distance. So that's going to be the force, which is the projection of F onto PQ. And then the distance would be the vector PQ. Okay. The projection of F onto PQ was equal to, the magnitude of that was equal to the magnitude of W1, and the magnitude of W1 is equal to the magnitude of force times the cosine of theta and times the magnitude of PQ. Well, I'm going to write it up at the top here. Recall that the cosine of theta is equal to, so cosine of theta is equal to u dot v, that theta being the vector, the angle between u dot v, over magnitude of u times the magnitude of v, or the magnitude of u times the magnitude of v times the cosine of the angle in between u and v is equal to the dot product. And so that's exactly what we got here. We got the magnitude of the force times the magnitude of the vector PQ times the cosine of the angle in between the force and the PQ. And so we can make that replacement, and we simply get F dot PQ. And that's going to be the easiest to calculate out of the bunch here. Okay, let's go ahead and look at one example, and that'll wrap up this section here. All right, so example number 7, it says, a shed is pulled by exerting a force of 100 newtons on a rope that makes a 25-degree angle with the horizontal. Find the work done pulling the sled 40 meters. So we'll just use a box to represent our sled. There's our P and there's our Q, and we're going in that's our line of direction that we're moving. Here's our force that we're going to be applying, pulling a rope at an angle of 25 degrees with the horizontal. So the work is going to be F dot PQ. So we just need to find the force vector and PQ, and then do the dot product, and we're good to go. All right, so the force, it's going to be the magnitude of the force, and then cosine of theta, sine of theta. So the magnitude of the force was 100, and then cosine of 25 degrees, and 100 sine of 25 degrees. All right, that looks good. So let's go ahead and install that. Okay, and then vector PQ, we can say that at P is the origin and at Q is 40 meters away, so that'd be 40, 0. All right, so when we do the dot product, we're going to get 4,000 cosine of 25, and that's going to be about 3,625.23, and that would be newtons times meters, Newton meters, and I believe that is also a joules. We call those joules. All right, so that wraps up section 2.3, and stick around for 2.4. We'll see you next time.